Here we go with an example. Now, as we read this example, we're gonna sort of discover more connections between these hyperbolic functions and the original 6 trig functions. So a big part of the connection and why they ended up being named this way are because there are all these identities when it comes to the hyperbolic functions. Okay, as we see this, so in this example, we're going to prove this particular hyperbolic identity that cosh of 2x equals cosh squared x plus sinh squared x. Okay, a lot of the hyperbolic function identities are very similar to the trig identities, sometimes with as little as like a plus sign instead of a minus sign or a minus sign instead of a plus sign. So you would never expect this from the way these things are defined, using E, but it worked out that way. That said, these identities, it's not a major part of our section. Okay, it's really just part of the discovery of why they're named what they are, and we're just getting to know these functions before we start looking at the calculus of them, which is appropriate. We don't spend a lot of time on it, but a little bit is good. Okay, so we're going to prove this hyperbolic identity. How are we going to prove this? Okay, actually, if you were traumatized by the trig proofs when you took trig, these aren't going to be maybe nearly as challenging. It's really boils down to algebra. Okay, why is that? Because these are all defined in terms of e to the x or e to the negative x. So here's what we're going to do to prove this one. I'm going to write both sides. I'm going to rewrite them using their definitions. Okay, so if you remember, cosh x was e to the x plus e to the negative x over 2. And so we'll need that here, we'll need that here. And if you remember, sinh x, same thing, but minus in between. Okay, so just using these definitions, let's rewrite these both. And I've done that here. Okay. So what just happened? All right, well, cosh 2x. Well, that just means I'm putting a 2x, right? E to the 2x plus e to the negative 2x over 2, right? That's cosh 2x. On the right side, cosh squared x plus sinh squared x. Well, that's cosh x, and then it's being squared, plus sinh x, and that's being squared. So I'm just going to write both sides from their definitions. And then what's my job after that? Once I've written these out with e to the x and e to the negative x and such, what do I do? Okay, so here's my advice. We're going to simplify the more complex side to equal the simpler side. Okay, so what we're going to pick which side is more complex. Is this side more complex or is this side more complex? Okay, so hopefully you guys are with me in that the right side here is more complex. There's more going on. By complex, I mean there's more to simplify. I mean over here, you can't simplify this, right? What do you do with that? But this you can simplify, right? We can square things, then we can add common denominator and that sort of stuff. There's stuff to do here. Okay, so we're going to pick the more complex side. We're going to simplify it. And when we're done simplifying, we're just going to cross our fingers. Hopefully it turns out to equal what it should. And well, if this really is a true identity, then yeah, that's going to work out that way. Okay, so I'm picking this side, so I'm just focused here, and I'm just going to start doing whatever I can. I'm going to square, I'm going to add. All right. So you notice I'm just leaving the left side here blank. I've got just copying the equal sign, and I'm going to start to simplify. So what did we do here in this first line? I put the square on the numerator, squared the denominator, numerator, denominator, just like that. Okay, starting to simplify. All right, what are we going to do from there? Let's multiply out both of the numerators. Okay, let's slow this down just a bit. I'll give you a chance to read it, copy it. Let's look at this first numerator. What happened? Okay, so we're going to FOIL here, right? So I'd say e to the x times e to the x. And that would be e to the 2x, right? Because you add the exponents. E to the x times e to the x is e to the 2x. Where did this plus 2 come from in the middle? Now that oftentimes is strange to people. Well, that's the two middle terms put together. So what happened there? I had e to the x times e to the negative x. I'm going to write that here. E to the x times e to the negative x. Well, what happens e to the x times e to the negative x? Well, we add the exponents, right? But in this case, when you add them, you get 0. And so you get 1. So e to the x times e to the negative x is e to the 0, which is 1. And that's going to happen twice for the two middle terms, and hence why you have plus 2 there in the middle. And then finally, e to the negative x times e to the negative x, we add the exponents again, right? And we get e to the negative 2x. If you need to work that out and FOIL it out, certainly do that on the side. If you don't quite follow this FOIL, by all means, show more steps or kind of justify this one to yourself. If this one makes sense, this one, very, very similar. So we've got e to the x times e to the x. Well, we've got the e to the 2x again. We've got e to the x times negative e to the negative x. Well, then that would end up being negative 1. And that happens twice for the middle terms, so we have a negative 2 there in the middle. And then finally, negative e to the negative x times negative e to the negative x is positive e to the negative 2x. And of course, it's all over 4. And there's the right side all squared out. Okay, from there, hey, we already have a common denominator. Let's just add the numerators. And they actually add very simply, right? E to the 2x plus e to the 2x, 2e to the 2x. Positive 2 and negative 2 go away, cancel. E to the negative 2x, e to the negative 2x, 2e to the negative 2x. And it's all over the 4. We're almost there. We can simplify just a little bit more. You notice that each is a multiple of 2. So let's divide by 2 everything. And we'll get e to the 2x plus e to the negative 2x over 2. And that's where we started. Maybe, just to be very, very clear to finish this off, I'm just going to say that that is equal to cosh of 2x. And if we kind of go back to see the whole problem, all this worked out. Really, we could have even started here. If we noticed this was the more complex there, and not even written this part, just there to there to there to there, and all the way down until we get it to equal cosh 2x, and then, it's like we're saying cosh 2x equals cosh 2x, and we got it. Check. Okay. We're getting to the calculus still. We're not there yet. Let me erase some of this scratch work I had there. All right. While we're talking about identities, I want to list the 3 most important hyperbolic identities, and they might look very familiar. The 3 most important, or the 3 basic hyperbolic identities, are very similar to the basic trig identities. We call them the Pythagorean identities in trig. Okay, so the first hyperbolic, cosh squared x minus sinh squared x equals 1. You may remember I know you do because we've seen it in this class. Cosine squared x plus sine squared x equals 1, right? That's the Pythagorean identity with cosine and sine, and it's a plus in the middle. The only difference here with the hyperbolic, it's a minus. And now this second one might look familiar. 1 minus tanh squared x equals sech squared x. Identical to the trig identity, 1 plus tangent squared x equals secant squared x, except for that minus sign instead of the plus. And finally, coth squared x minus 1 equals cosech squared x. Again, identical except for the minus instead of a plus. And so when people started to realize this, then the name was just an easy call. So they named these the hyperbolic trig identities, or oftentimes you just hear it called the hyperbolic identities for short. Okay, let's discover where the name hyperbolic comes from. What's up with that? There's also a connection to the hyperbola, right? So it's based on E. It's got all these similarities to the trig functions, but it's really rooted in the hyperbola. What is this? This is nuts. All right. There's a reason I just show you these identities, okay? It's all going to tie together, okay? So think about the general hyperbola, all right? You would have done this in algebra. It's not right there at the top of your memory. I understand that. But here's the general form of a hyperbola, okay? X minus h squared over a squared minus y minus k squared over b squared equals 1. All right, this thing is centered at hk, and the a and the b are necessary in order to draw that parabola, draw the graph. Okay, so that's the general hyperbola. Let's talk about the unit hyperbola. Okay, so what's the unit hyperbola? The unit hyperbola is centered at the origin, and both the a and the b equal 1. Okay, so if a equals 1, b equals 1, and it's centered at the origin, that equation would reduce to just x squared minus y squared equals 1. Okay. Hey, do you remember the unit circle? The unit circle is x squared plus y squared equals 1, where there's a plus instead of a minus. Oh, and this is what all of trig is based on, the unit circle. So the unit hyperbola is what all of the hyperbolic trig is based on. But how? Okay, we haven't quite seen it. Here's a graph. This is going to do it for you. Okay, so think of the unit hyperbola. So since the x comes first, it opens up horizontally, if you recall that. And the unit means the vertices here are at 1 and -1. Okay, and it's this nicely shaped hyperbola. Since it's the unit, it's not overly narrow or overly wide. It's got this just the shape. It's hard to sketch, obviously, but it's not too narrow, too wide. It's right there in the middle. Okay, so what's the deal? Okay, so the unit hyperbola. Notice the connection between this first identity here and the unit hyperbola, right? X squared minus y squared equals 1. Cosh squared minus sinh squared equals 1. Over here on the side, let's say x is equal to cosh. Now I can't use x again, but maybe I change this variable. Usually what people do is they make it a t. So think of this as cosh squared t minus sinh squared t equals 1. Then this x would equal cosh t, right? And y would equal sinh t. So the idea is any value of t that you pick any value of t you want. If you put it into cosh, you're going to get the x coordinate of a point on the hyperbola. If you put that same value into y, you're going to get the corresponding y coordinate of that point. Pick any value of t that you want. Put it in here. You got the x coordinate of a point on this curve somewhere. Put the same value into sinh. You'll get the y coordinate of that same point. So this is the graph of every point defined by cosh t sine t for every value of t. That is pretty cool. You can do the same thing in trig, right, with the unit circle. I don't know if some people teach things differently or emphasize different things. If you go with the unit circle, x squared plus y squared equals 1, any point on that circle could be thought of as cosine t sine t. Take the same value, plug it into cosine, you got the x coordinate, plug it into sine, you got the y coordinate, and you can create every point on that circle by picking values of t like that. Oh, so the connection to the hyperbola. Okay, that's all of our background. In the next video, we're gonna do derivatives.